Let's have a look at an example of creating transformation parameters. So here's an example where the country of Fiji had a datum in WGS72. So this was a precursor to the WGS84 that we've been talking about. And the Pacific Islands Applied Geoscience Commission, which is a regional group similar to sort of RCMRD provides for parts of Africa, they do this for the Pacific Island countries. There's sort of that point of expert advice and assistance within the region. And they asked Geoscience Australia to compute ITRF coordinates at 18 different sites on the islands in northern Fiji using GPS measurements that they'd captured between 8th of July and the 5th of August. So you can see this is like a month-long campaign. It's not continuously operating reference stations. It was just 4 weeks worth of observations that they had taken. And these coordinates, the main reason for doing this is because and this is another good resolution or reference that you can use. Countries wanted to understand and extend their claim under the UN Convention on Law of the Sea. So a big part of life in the Pacific is the ocean. They don't talk about themselves as being small island developing states. They call them big ocean states. More of their land mass, more of the area of the earth that they have exclusive economic rights over is covered by ocean and navigation and offshore mining and oil leases and things like that, rather than being the stuff that's on land. So the Convention of the Law of the Sea is extremely important to them. And they wanted to make sure that they had coordinates in a modern reference system so that it could be acknowledged under the United Nations Convention on the Law of the Sea. So that gives you the context of why this was being done. Again, the why is very important before you start doing anything. So they wanted to move, as you can see at the bottom there, from WGS72, and the static datum they wanted to work in, because that was what's used by the Convention on Law of the Sea, was ITRF 2005 at the epoch of 2008. So we were helping them compute this 7-parameter transformation in the middle. Here's an example of where these stations are. Sorry, Israel, we're using Google Maps to show where this is. Google Earth, sorry. So it's pretty close, but it's not exactly right. So they had 18 stations where they observed this data. They had dual frequency observations. So that's very important. They were capturing L1 and L2. That's what you need to get the very precise measurements. And they recorded for 28 days continuously on these marks. Now, they chose these marks because they had very good information about them in WGS 72. So they already had the original coordinate set on these 18 points, and they wanted to capture the ITRF coordinates so that they could compute the transformation. So to process the data, which was the next step, processing the GNSS data to compute the ITRF 2005 coordinates, they included IGS stations. Now, at this time, what they did was include 5 IGS stations from the surrounding area. And as we learned yesterday, that allowed them to align all of their work within the ITRF, because if you're linked with the IGS stations, you're going to be linked with the ITRF. They also included Pacific Island regional reference frame sites. So this is the regional information that comes out of APREF, the Asia Pacific reference frame. They included information from those sites as well. So that's adding density to your data set, and it's improving how accurately you can compute things like atmospheric conditions when you're recording information at the same time. So again, that's going to improve the quality of the solution that you get. And here's the outputs. On the left-hand side, you can see the original WGS72 coordinates in X, Y, and Z. And then on the right-hand side, the ones that I've highlighted are the same points, those 17 or 18 points, along with the extra ones. But the ones highlighted are the ones that are matching the ones in the table on the left. So we now have our X, Y, Z in WGS72 and in ITRF 2005 at the epoch of 2008. Now here's our equation again. So on the left-hand side, you have your XYZ ITRF 2005, and on the far right-hand side, XYZ in WGS 72. And we're trying to solve for the translation, the scale, and the rotations between these two different frames. So you need at least 3 common points to do this, but I would highly recommend you have more than 3. The more, the better. And you will see this when you start doing your validation, as Professor Lazarus mentioned before. If you've got more data going in, high quality data at the start, if 18 is going to give you a much better result than 3 for the Fiji area. And what it does is it solves what they call a linearized system. So you set up the equations, and I found a great article this morning where maybe you were involved in this, Professor, in 2019 with the Nigerian example with the development of the transformation parameters. There's a great article that's been published that shows how this has been done for Nigeria. So I'm going to email that around after this session, and it shows you the steps that you go through mathematically that I'm summarizing here, where you're solving for those parameters. You're then iteratively refining them. So it's not a one-off solve process, because you're actually trying to find, how do I minimize the errors? How do I minimize the residuals? So you go through and you continually refine your information, and you reprocess, and then eventually you find out that the residuals are minimized, and that's when you know you have the most accurate parameters that are coming out the other side. So this is called an inversion process. And then, as we talked about, you verify it. So how do I check that these numbers are correct? You can do that using what they call a bootstrap method, where you can take one point out and then compute the analysis and then use that as a test point. But it's better if you have independent points that you can use as validation techniques. So here's our set of coordinates in the 2 different frames. And then here's the results. And I've done a set of results using AI, just for fun. Can AI, I went through this process with ChatGPT, and I said, right, I want you to compute the transformation parameters for me using this input data set and this output data set. And the results on the right-hand side are the ones that came out of a scientific paper produced by my colleagues, John Dawson and Grung Hu, and I trust them because they're much smarter than me. And they came up with results that are shown there that give the translations, scale factor, and the rotations. And you can see the residuals there at the bottom. So in the X, Y, and Z, if you're looking at how well these transformation parameters work for Fiji, X, Y, and Z, you're looking at residuals of about 1 meter in the X, Y, and Z, 0.8 to 0.9 of a meter. I asked ChatGPT to solve this solution as well. I didn't feed it the equations. I just said, I want you to tell me the transformation parameters. And it went away to think about how you could do this. And the interesting thing is, when I originally did it, it got very wrong results. So for those of you who say AI is not going to solve the world's problems, you can say, well, it didn't fix it the first time. But what I could do is I could train the AI. And this is something that Ryan and I and some of my colleagues in the center are talking about. How do we train an AI system with intelligent information and professional judgment that we all have in the room to say that could be right or that could be wrong? If you give it more information. So over time, I gave it additional papers, scientific papers it could read about how to do this properly, how to verify it, how to validate it. And as I trained the model, I got to a point that on the left-hand side, it came up with results that they're slightly different, but they're within the residual realm of what you get from the professional work that was being done by John Dawson and Grung Hu. So what it shows is that we're talking about the need for capacity and developing capacity. What we're looking at doing is, can we start training some of these systems and make tools and AI systems available to a broader community where you're using a trusted source of AI. So you don't need to write the software or be an absolute professional in every aspect of developing transformation parameters, but you know what looks right or looks wrong. and is within the realm of what is reasonable. And it shows that if you train the AI correctly, it becomes a much easier way for you to compute these type of transformation parameters for your country. And this could be applied to other parts of Geodesy as well. And here's the code. So there's the code that I use to compute the transformation parameters. And I didn't write this code. It's written in Python. I know a little bit of Python, but I don't know what some of these calls are or some of these libraries that it's using. But it developed this. So once I had the right result, I said, can you print out the Python code that you use to compute these transformation parameters? So this becomes something that is then repeatable. I can show people what was done to the data, and I can go through the steps and ask whether or not that's a reasonable approach. So you don't even need to be an expert in software development. You can ask the software, you can ask ChatGPT or any AI to say, print out the software that you use to compute that. So some questions. These, you don't need to be restricted to these. We've got about 20 minutes before we're breaking for morning tea, but I'd be interested to know, have others started thinking about using AI? How could we validate this, as we've talked about? And then who else could you ask for assistance? I mean, I talked about us developing some sort of Geodesy chatbot that you could feed information into and hopefully get reasonable authoritative answers out of it. But how else do you think we could do this, or what kind of things would you like a chatbot to be able to do for you? So with that, I'm happy to open the floor for questions or discussion. Thank you.
Thank you, Nick, for the presentation. And I am speaking about the rotation. When we determine rotation, there is two main methods: the position vector and the coordinate frame rotation vector. So usually when we determine parameter, we are going to use them in RTK surveys. So we should be very careful when introducing rotation parameters. We take care of the method used, because it will give erroneous result if we introduce them incorrectly.
Thanks, Sahir.
Thank you, Nick. Like you were saying, while using AI, you had to feed it as papers before, so that it gave you the result that were more accurate. So there's something called prompt engineering. So prompt engineering is something like you have to feed the AI with certain parameters, certain calculations, so that you get slightly more correct answers or even accurate answers. Thank you.
I like the way you describe that. Hopefully we eventually get to accurate, but we need the professionals to check it. So yeah, good point. Thank you very much. Jack.
Yeah, so regarding AI, I think one thing that everyone has to be careful about is when, like, you can train this, but you can also get it to hallucinate, but it's essentially diverging from right answers. So this is where, as you say in here, the validation step is the crucial part, where, if you don't have the experts in your country yet, and you get a result and you say, okay, this must be right because of AI, there shouldn't be initial trust in that. Yeah, hallucination is a bad thing. We have it in astronomy as well. And you basically get objects in the sky which don't exist, but the AI thinks it's there because you've trained it on something that isn't completely the same as what you have in your data, because it might change a little bit.
I think astronomers had it in AI, had it before AI. They had hallucination. Thanks, Jack. Yes.
Actually, my question is going back to what we saw in Australia. When I saw the velocity field were moving more or less with the same velocity all over. So this seems that Australia is stable everywhere. So what is then the essence of having the time dependent? Why don't we put a static? Because even if we go, it doesn't change the position of the plots or rods, whatever. Why don't they stay with a static? Yeah. And another thing is, when you are transforming from one system to another system, the way we saw in Africa is that they have different, the legacy frame is actually have different problems. And there is no way you can transform to a unique reference frame without having these residuals, large residuals. And then how much residuals can be then accepted that we can use and accept in our system, that then we can go with it. Yeah, thank you.
Have a look at step 1 of the roadmap. The residuals you can accept is dependent on your user requirements. You need to talk to your users. You need to know what the applications are, and you can't develop a technical solution until you know what your user requirements are. So that bit's quite simple. Regarding the why we went down the path of having a time-dependent frame as well as a static datum is because, as I showed you, there's still distortion. When you take out the plate motion of 7 centimeters a year, it does most of the work quite well, but it doesn't remove all the differences between real-time positioning and what you would get in GDA 2020. So it covers most of the difference, but there are still internal distortions that for some very high accuracy applications, users want to work in, they want to work in the same reference frame that they're receiving information in real time from the GNSS systems. They don't want to have to go through GDA 2020 and convert it back and forth, because that's going to increase the amount of error in their data set, and they're trying to avoid that. Izzy and then Aslam.
So trying to buttress what he said, I observed that in Australia, because of that time-dependent system you have, because of the shift, because of the velocity, that's why you're having that. But in Africa, I also observed that we're having the plates are like not shifting. We are having a very, we are not having like, how do I say it? Our plates are stable, they crossed. So I'm now asking, is it better that we're having a static like in Africa because of the static plates that we, you know, they are the crust of Africa, you understand? Do you advise us to have a static, what's that, datum? Which word will I use? Like you said, time dependent and static. So what are you advising in Africa?
I'm advising you to talk to your users. You need to talk to your users. It's not up to me to decide what reference, whether you have a static regional frame or a static national datum or a time-dependent datum. I don't know what your users want. You need to talk to your users, and that's step 1 in the roadmap. It's not technical, but you need to ask them. And you don't ask them, do you want a static or a time-dependent reference frame? Because the people who run the road network, they go, what are you talking about? You need to understand what their jobs are, what they need to deliver, what kind of accuracy. And the answer in one country might be different to another country. We heard from our friends in Ethiopia yesterday about the challenges of monitoring the Rift Valley, because they're seeing deformation happen through that region. So some users in Ethiopia might need a time-dependent reference frame for dealing with some of the issues they have. You are the experts in the technical, but you are not experts in how everyone uses the datum. And you will never be experts in how everyone uses the datum, but you need to have a better understanding about how people use the datum, because if you don't, you're not going to get financial support to keep doing the work that you're doing. You do this on behalf of the users of the datum. Without the users, you don't need to exist in the government's eyes. So you need to engage with that community and get them to realize that they depend on you and understand what their requirements are. Aslam.
Yeah, thank you, Nick. With regard to residuals, I would just want to reflect on our own personal experiences with the reality is, you know, when you're trying to determine transformation parameter from the old datum to a newer, more modern reference frame that's far more accurate. A tendency of many people is to take out points to improve the residuals. So RMS going down from 10 to 5, but what you're actually doing is it's really counterintuitive. I mean, it's exactly the opposite of what you need to do, because you're trying to model the relationship between system A and system B. You fool yourself now, and a lot of surveyors have they fool themselves, and they say, okay, take out this beacon and that beacon and that beacon. Eventually, it becomes a very one-sided transformation, and just for the sake of having improved results. So unless the beacon is proven to be destroyed, or that is the reality, is that our old historic datums had distortions, and as far as possible, unless one can determine that that point was disturbed, that was a reflection that the datum is realized by the coordinates of those points. And so this is something that must always be taken into consideration, that when one computes transformation parameters, be careful of removing points to the extent that you're actually then not having a real relationship between system A and system B. Thank you.
Yeah, good point. Jack, that's when geodesists start hallucinating. They start taking points out, because you should never do that. We've got time for one more question before I want to break. Yes, thank you.
Merci, Nick, pour cette.
Thank you, Nick, for this presentation and the perspective of going towards AI. But our issue is AI is that it never says no, and it also needs a different context. Have these models been experimented on different contexts and different scenarios, without speaking of the infrastructure which they need and the connectivity and everything else related to it in order to generate this data? Thank you.
Sure, just one moment. That excellent point, and I'm being deliberately provocative to bring up AI in this forum and talk about how it can be used, because I want us to have this discussion. I want us to realize that we need to be very smart and validate the way that we do this, but also to show that if you do it the right way, it can be done. So we can't keep doing things the way we have been doing things in Excel spreadsheets and text files. We need to modernize the way that we work, because we need to understand that that's what the workforce in the future is going to be doing. So if we want to capture people coming in and working in this field, they want to see that we're using state-of-the-art technology. So we do need to use AI, but we need to be very careful about how we do it. And it's going to be the professional judgment of all of you in the room that is going to help us guide the development of the models and the processes that we can use and we can trust. But so thank you for that comment. Yes, thank you.
Thank you, Nick. Just a rider to what Aslam said. It is very important for us to consider the technical requirement before we start computing transformation parameters. One of the technical conditions is the geometry of the locations of those controls, so that you avoid lopsided computation. Because if you do that, you are going to get erroneous. So it is important you do internal consistency check within the coordinates you have, and be sure that these coordinates have been checked properly. We cannot avoid verifying some of 1, 2, 3, 4 of those coordinates that are used as fiduciary as a control for you to actualize this work. If you don't do that, because in Africa, like she said, it's not true that Africa is static. I think Saria has a good authority on that. We have intraplate motions. One of my PhD students did a work. His research was on lithospheric motion in Africa on Nubia plate. It shows it just limiting it to Nigeria. That's tell that within the country, you have distortions here and there. So we don't assume that anything is static, but we can have an initial approximation and move forward. But doing that, you must ensure that the coordinates you are using, they are geometrically well distributed, and you are sure they have internal consistencies. If not, you are going to have something that you deceive yourself, like Absalom said.
Yeah, thank you. Great points. All right, let's break now for a coffee, and we'll come back in here at 11 o'clock. Thanks, everybody.